How are you, all of you? I hope you are fine. Have you seen the previous videos what I have uploaded on the e-learning site? In today's class, we'll see about color coding and standard resistors values, Ohm's law, series parallel, and series parallel of resistive circuit. The first subtopic is color coding and standard resistors values. Have you seen a small resistors which have different color codes printed on them? Yeah, such types of resistors are their magnitude are defined by this color coding. A wide variety of resistors, fixed or variable, are large enough to have their resistance in ohm printed on the casing. Some, however, are too small to have numbers printed on them, so a system of color coding is used. A bands may have 4, 5, or 6 bands may be used. Let's see how can we determine a 3 or 4 band resistor values. In this band, the first two bands always denote the first two digits of the resistance value in ohm. The first two bands always denote the first two digits of the resistance value on ohm. On a 3 or 4 band resistor, the third band represents the multiplier. The third band represents the multiplier, and this multiplier will basically shift your decimal place around to change your value from mega ohm to milli ohm and anywhere in between. The fourth color band signifies tolerance. The fourth colored band signifies the tolerance. The tolerance. The fourth one will represent the tolerance. For the time being, if you have such types of printed printed resistance which have uh, four bands, if the first one is red, this indicates the first digit, and if the second one also red, this will indicate the two digits, the two digits, and the third one is your multiplier. Your multiplier, if it is black, this indicates your multiplier, and the last this one indicates your uh, tolerance. For the time being, if such types of resistors are there, that means the first and the second are red. That means if it is red represents 2 2, so 2 2 it will be 22, and the multiplier is uh, black indicates 10 the power of 0, so you will multiply 1, and this gold color is the tolerance. So the tolerance means you will have plus or minus 5%. So this is 20 ohm resistor. So you can calculate easily like this one. You can calculate easily the values of a resistance like this. There are tables which indicate the numberings for the time being. In this table, black indicates the first digit. If it is black, it will be 0. If the second digit is black, it means 0. If it is brown, 1. If it is red, 2. If it is orange, 3. These are the tables. And when we come to the multiplier, if it is the first one is black, 10 to the power of 0 means 1. 1. If the multiplier is brown, that is the third one, it will be 10 to the power of 1. That means you will multiply by 10. If it is red, you will multiply by 10 to the power of 2, that is by 100. And when we come to the tolerance, if it is a brown, you will have plus or minus 1%. And if it is green, plus or minus 0.5%. And if it is gold, plus or minus 5%. So by using this table and according to the color coding, we can get the magnitude of the resistors, a color coding resistors. So this is what it seems like. The first two digit indicates the first two band indicates the first two digit, that is XY, and the third digit is the multiplier. So you can easily get you will multiply by the multiplier and plus or minus the tolerance. For the time being, if the register band is the first one is red, the second one is red, and the third one is the black, and the last the tolerance range is gold. So red means You can read from here. Red means 2. The second band is again red, so 22. And the multiplier is black. Black means 10 to the power of 0. So this value is 22 ohm with tolerance of plus or minus 5. So if the resistor have a 3 or 4 band, you can easily get the values of the resistance by using this formula. What if the resistors have a 5 or 6 band? A 5 or 6 band, how can you determine the value of the resistance? A resistance with high precision have an extra color band to indicate the third significant digit. If your resistance have 5 or 6 color bands, the third band becomes this additional digit along with the band 1 and 2. Along band 1 and 2, the third digit become the digit band, additional digit. Everything else shifts to the right, making the fourth color band the multiplier and the fifth the tolerance. The fifth will be the tolerance, and the sixth band resistor is basically a 5 band type with additional ring indicating the reliability of the temperature coefficient. So it will be the temperature coefficient. The last band will be the temperature coefficient. And let's show you what it seems. Does it mean in the board? For the time being, you may have. We are talking about 6 or 5 band resistors. So 1, 2, 3. This is a 6 band. 1, 2, 3, 4, 5. A 5 band actually. This is so the first. This is the first band, and this is the second band, and this is the third band, and this is the fourth band. And let's change the color. This one is the fifth band, and this one, the last, is the sixth band. So let's say this one is X, Y, Z. So the first 3 digits, the first 3 bands indicates the digit X, Y, Z. And the fourth one is the multiplier. You will multiply by, let's say this one is A. A is the multiplier. And the fifth one indicates the tolerance, plus or minus. And the last one is, this one indicates the temperature dependence. Of, as you know or you may not, the resistance will depend on the temperature. So this is what I have already defined. We can get the 5 or 6 band resistors by using this formula. For the time being, this is an example. The first one is red, the second one is violet, and the third one is yellow, the fourth one is black. So the first 3 are the digits. You can check from this table. Red means 2, and violet means 7, and this yellow means 4. So 274 times. The multiplier is black, so you will multiply by 10 to the power of 0, 1, and red. When we see red, red indicates the tolerance. That means the fifth band is the tolerance. So the tolerance is, as you can see, plus or minus 2%. And the last one, the black, indicates the temperature dependence, the temperature coefficient. So this resistance value is 274 ohm plus or minus 2, and with parts per million or per degree Kelvin. That means the dependence. What is Ohm's law? The next topic is Ohm's law. Ohm's law states that the current I flowing in a circuit is directly proportional to the applied voltage V and inversely proportional to the resistance R, provided that the temperature remains constant. If the temperature varies, the resistance, this relation will not true. Ohm's law states the relationship between electric current and potential difference. The voltage across a resistor is directly proportional to the current moving through the resistor, the current moving through the resistor. We can indicate graphically like this. We can indicate graphically like this. The resistance is a model and it will not produce a straight line or a condition of operation, but we have fixed that the temperature is constant. The temperature is constant. Since the temperature is constant, at constant temperature, according to Ohm's law, we can get such values. We can get such relations. This is the relation which indicate Ohm's law. Ohm's law. If we see graphically, we can see it seems like this one. That means, let's say this is XY relation. So if it is this like this one, this is a straight line relation, a straight line relation. As already it is indicated here, it will be a straight line relation, the other thing is to memorize Ohm's law, we can use this Ohm's law triangle. We can use this Ohm's law triangle. For the time being, this is the Ohm's law triangle, what it seems like. Let us show you here. The Ohm's law triangle is, this is a triangle. So let's divide into some parts. This is I, this is R, and this is V. So this is division. This is division. We have put division, and here it is multiplication. So from this graph, we can easily, V means I times R. And if we wanted to I means V over R. And if we wanted to R means, if we want to get R which is equal to V over I. So this Ohm's law triangle used to easily memorize the relation between the voltage, the current, and the resistance. The voltage, the current, and the resistance. We can easily memorize the relation between the voltage, the current, and the resistance. Not only this one, but also we can memorize the relation between the power, the current, and the voltage. The power, the current, and the voltage. Let's show you this one also. From the Ohm's law triangle, you can easily see that this is another triangle. This is P, this is I, this is V. This is I, this is V. As I told you before, in the vertical arrangement, this is division. And in the horizontal relation, it is multiplication. So you can easily get the power P, which is equal to I times E. If you wanted to know the current and you have the known values, power and voltage, you can easily get current I means power P over V. And if you have the power and the current are known values, you can easily get V means P over I. So these two these relations, power triangles, Ohm's law triangles, are used to easily understand or to easily memorize these relations. What is current? According to Ohm's law, what is current? Under the influence of an electromotive force, the one valence electron of each copper atom is pulled from outer orbit and moves through the copper space towards a positive potential. If you have a potential difference here, so the positive charges will come to the negative terminal and the electrons move to the positive terminal. So electrons move towards the positive terminal of the electromotive force. Conventional current flow assumes positive charges move towards the negative side of the AMF. So by the rule of repulsion, this potential will push positive charges to this negative terminals. The negative terminals. Actually, the protons which are located at the center of the atom are not movable, but we can think about relative motion. Relative motion. That is, the movement of electrons are, in other words, the movement of while we are talking about relative motion, it is a movement of, we can say, positive charges, positive charges, positive charges, positive charges. So it can move from the positive terminal to the negative terminal, the negative terminal. So always when we say the currents are moving from positive to negative, that is the movement of electrons, the movement of electrons that is from negative to positive, but the movement of protons or positive charges are from positive to negative, positive to negative. So conventional current flow assumes positive charges move towards the negative side of the circuit EMF, as you can see here. This is the current what Ohm's law are related. Ohm's law are related. What is the series parallel and series parallel of resistive circuit? Resistive circuit. Let's see. How can we relate? How can we connect resistors in series? Resistors in series. As you can see here from this image, the figure below shows a resistors connected to a battery. These two resistors are connected to a battery. Since there is no junction, the current I must be the same in both resistors. The current, there is no any junction or branch circuit, so the current passing from R1 is the same to that of R2, the same to that of R2. If we replace two resistors with a single resistor having the same value, that is R equivalent is equal to R1 plus R2, the total potential difference across this resistor is still E, because the potential difference is established by the battery. There is any losing circuit in between the two, So if the current in the single resistor is, which is equal to E over R equivalent, E over R equivalent. R equivalent means the summation of the two resistors, the summation of the two resistors. The single resistor is equivalent to the two series resistors in the sense that the circuit current and potential difference are the same in both cases, the same in both cases. If we have n resistors in series, their equivalent resistance is the sum of n individual resistors, n individual resistors. This means R equivalent is equal to R1 plus R2 plus Rn. This is how can we determine the equivalent resistance of a series connected resistors.